Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 14, 2025, just yesterday. This paper presents a framework that allows a model with nearly 50% fewer parameters to achieve higher accuracy than a standard baseline. The paper is titled Mixture-of-Recursions, Learning Dynamic Recursive Depths for Adaptive Token-Level Computation, and it shows an effective path towards getting large model quality without the large model cost. It unifies parameter sharing and adaptive computation, letting the model dynamically decide how much thinking to do for each token. Also, the authors shared their work on GitHub. For those who want to check it out, the repository is currently live with the essentials like the README and license file. It looks like the full implementation is still on its way, but you can definitely go start it to follow along. So, to really understand how this works, let's look at the first figure. It gives a great overview of their Mixture-of-Recursions framework. On the left, you see the core idea. A small component called a router decides if a token, which is just a piece of text, needs more processing. If it does, it's sent through a shared stack of layers again. This is the recursion part. The chart on the right shows the result. Some tokens get computed multiple times, shown in dark blue, while others are skipped, saving computation. Building on that idea of recursion, this next table gets into the specifics of how the model shares its layers. This technique is called parameter sharing, which is essentially a way to reuse parts of the model to keep it small and efficient. The table compares two approaches. The cycle strategy on the left just loops through all its layers repeatedly. But the middle cycle strategy on the right, which they found works best, is a bit different. It has a unique first and last layer, and only reuses the layers in the middle. Alright, so that's how the layers are shared, but this figure gets into how the model actually routes tokens through them. It shows two main strategies. First is expert choice routing, where at each recursive step, a router selects the most important tokens to continue processing, progressively narrowing the focus. The other is token choice routing, which decides a token's entire path from the start. They also show two KV caching strategies. KV caching is a technique to store key intermediate calculations, which helps save a lot of memory and computation. Moving to the results, this table really shows the payoff of those strategies. It compares their Mixture-of-Recursions model, or MoR, against a standard vanilla transformer and a simpler recursive one. They measure things like negative log likelihood, which tells you how well the model predicts text. Lower is better. They also look at few-shot accuracy, which is how well it learns from just a few examples. The key takeaway is that the MoR model, with expert choice routing, gets a higher average accuracy, 43.1% than the vanilla model, while using nearly 50% fewer parameters. So these charts really drive home that efficiency point. We're looking at 4 plots, each for a different model size, from 135 million up to 1.7 billion parameters. The goal here is to get the lowest validation loss, which is a measure of model error for a given compute budget. And across the board, their Mixture-of-Recursions model, shown in orange, consistently achieves the lowest error. This is really impressive because it does this while using significantly fewer parameters than the standard vanilla model, showing it learns more effectively with less. And this efficiency isn't just about training. It translates directly to faster inference speed. This next set of charts breaks that down. The plot on the left shows what's called a Pareto frontier, which is just a way of visualizing the best possible trade-offs between model quality and throughput, or how fast the model runs. We can see that their Mixture-of-Recursions models, especially MoR4, achieve much higher throughput, over 2 times faster, without sacrificing performance. The other two charts reinforce these findings, confirming that their middle cycle sharing and KV caching strategies are highly effective. So to wrap things up, what we've seen is a really clever way to tackle the massive computational cost of large language models. The key idea here is to combine two efficiency tricks, reusing the same set of layers over and over, and letting the model dynamically decide how much work to do on each individual token. This approach, called Mixture-of-Recursions, means it can achieve better performance and run over 2 times faster, all while using about half the parameters of a standard model. It really redefines the trade-off between model size and quality. That's all for this edition of the AI Research Roundup. Thanks for tuning in.